Hi everyone, welcome to our hands-on on how to tame virtual machines using SUSE Manager. I'm Cédric Bosdona, Senior Software Engineer in the Virtualization team at SUSE. And my colleague, João, will present the monitoring part and he will introduce himself in more details later. Our agenda today will have first some virtualization basics, real quick information, no deep dive or whatever. Then another look of the lab, which machines we have, what are the names. Then we'll start with the virtualization exercises. Once done, there will be some presentation, small presentation on monitoring and Prometheus and Grafana, and then the exercises about it. SUSE Manager has a virtualization add-on since SUSE Manager 4.0. This is typically an add-on type for systems. It is called Virtualization Host. We'll see later on how it translates into the user interface. It typically adds a tab, a virtualization tab on the system details, and it will allow you to manage your virtual machines on that system. The virtualization stack, the bottom of the stack is pretty known. libvirt calls Zen or KVM to spawn virtual machines. This is what Virt Manager uses already, or the Virsh command line. Here we'll be interested in the upper part of the diagram, where SUSE Manager uses salt. Okay, that's old hat, but salt also uses libvirt to spawn virtual machines, and we'll see how this is all combined together and what benefit we can take from it. The lab is composed of 4 machines, 1 server hosting the SUSE Manager server, 2 KVM hosts, KVM1 and KVM2. These have almost nothing, just OS, and that's all. And a monitoring machine that will host Grafana and Prometheus. The virtualization exercises are divided in 3 big parts. First, setting up Hypervisor, then creating VMs, managing VMs using the user interface, and then doing the same thing and more using soul states. Here we have the SUSE Manager. It's having the default configuration. And the only thing that we have prepared here is an activation key for sleep 15 SP1. That is all. So the first part will be to create virtual hosts and register them in SUSE Manager. So the machines are already prepared. They have a bridge interface that is named BR0, and all we need to do is register them and add the virtual host entitlement. There are 2 ways to do it, and we will see each of them. So the first way that we'll see now is to manually bootstrap the machine, and then afterwards add the virtualization host entitlement. The second way is to add the virtualization host entitlement in the activation key and then bootstrapping the system. So let's do the first one with KVM1. First we need to accept the salt key. So here in the list we just click this button, and then we need to wait for the KVM1 to be listed, but we need to refresh the page. So here it is. Just click on the and the link to see the system page. You can see here that this is a salt machine, a salt minion, and here we want to add a virtualization host system type. For that, we need to edit the properties. Click the virtualization host box, and this will add a virtualization tab here when updating. So here's the tab, and we'll see the virtualization host property here. So we will do the same for KVM2. So here I'm just editing the activation key and checking the virtualization host box here. This will add the virtualization host entitlement on all physical machines, not on virtual ones. So now the key has the property. It can just activate KVM2, wait for it, and then we'll see that it will have the type. So there it is. And here we already have the virtualization host type. There is one thing that needs to be done here after adding this virtualization host type, is that we need to restart the salt minion. This is due to limitation in the salt minion, and will allow for almost real-time changes in the virtualization list. So we can do that just by SSHing on the system, and then systemctl restart salt minion. We'll do the same with KVM1. Restart salt minion. Now that the two systems are registered and have the virtualization host entitlement, we need to set up the hypervisor on them. There are two options. Either you do it manually and follow the virtualization documentation and best practices, or you can use the salt formula that is provided with SUSE Manager to make it easier. So we'll go with the salt formula here. To add a formula, we just go to the one system, click on the formulas tab, and then click the virtualization host formula and save it. This added a virtualization host tab here, and there you have a few properties that you can change to set up the virtual host. So here we'll select the KVM, but you can have a Xen. You can enable default storage pool and network or not. Here we'll keep it. We'll keep the default values for the storage pool, but we need to use the bridge networking for our VMs. Otherwise, the Grafana and Prometheus won't be able to access the virtual machines, and then won't be able to monitor them. So we just check the bridge, set the name PR0, save, and then the formula enhances the salt high state. So we can see here the high state. In the high state, we can see the virtualization host packages that are added. We can see that libvirt will be enabled. The default pool will be created in var libvirt images, and we'll have a default network that will use the bridge PR0. Apply the high state. Can follow what is happening here and wait for it to happen. So now the system has been completed. Can go to the next one, KVM2. and do the same. Formulas, virtualization host, save, then visit the formula virtualization host, select the bridge network, save, go to the high state, and apply it, and wait. So now KVM2 is successfully installed. Our hypervisors and virtualization hosts are ready to be used. We could have done all these into one single step using system groups, but this will be demonstrated later with the monitoring. Now we are ready to create our first virtual machine in KVM1. So we'll click on that system, the virtualization tab. Obviously there is no VM yet, so we'll create one by clicking the create guest button. We'll just name it VM1. I'll reduce the number of the amount of memory because I don't have such a powerful hypervisor here. And we need to provide a source template image here. That can be a local path, but I already have an image, a juice image uploaded on the SUSE Manager server. So I'll just copy that link and paste it. This could also be the URL to a Kiwi built image using the image building feature of SUSE Manager. We could define a MAC address. Here we don't need it. We'll leave VNC as a graphic as the default. Spice can also be selected, but the graphical console is not that robust. And you can schedule the VM creation or add it to an action chain. That could be pretty useful to execute the VM creation after Kiwi image has been built, for example. Click the create button. Here we'll need to wait for the VM to appear. In a future version there will be an information message stating that a VM is being created. So now we have the VM. We see that it is running. Here we have a suspend action. We can have a stop, a restart. We can edit the virtual machine or delete it. But the action that is interesting us here is the graphical console. Since it's a juice image, we'll go through the first boot wizard. I'm French, pardon me, so I'll need to change my keyboard layout. As soon as the virtual machine will be started, we'll log into it and configure it to register in SUSE Manager. First, we'll give it a name, host name. And then we will add the activation key for Salt. So this is to be placed in these grains, the salt grains. It typically is a file in etc salt. This is YAML file, and we need to have a SUSE Manager item and a sub item. So here I added 2 spaces. It's YAML, indentation is important. Activation key, and here we need to pick up the key name from activation key here. Okay. We also need to tell Salt where to find a master. So we'll add a master.conf file inside the etc salt minion D folder, and just get a master property with our SUSE Manager server hostname. Now we need to start the salt minion. Systems control enable -- now salt minion. We can check in the salt keys. So here the VM01 is already here. We'll accept it and wait for the system to be listed. Here it is. So you can see in the systems the VM is already here. It's not yet completely initialized because the initial data are not yet fetched. It's seen as a physical machine, but it's not, and there's no package or patches updated yet. So after the initial update is done, this will be reflected correctly here. Okay. And in the KVM1 Virtualization tab, the link to the system will be also shown here. Now we will create a virtual machine using salt states. First, we need to SSH on the server and move into serve salt folder, create vms.sls file. This is YAML, so indentation and spacing is important. We'll first need to add to give an ID. So VM2 running, just it can be anything you like. And here you need to give the state you want to run. So virt.running here. This is what you can look for in the documentation, is salt documentation. And now we will give it some parameters. First, a name. So the name of the virtual machine. How many CPUs we want. How much memory in megabytes. What disks we want. Disks have a name. You can see here that I'm not adding a dash in front of that line because dash means list item, and this is just a property of the disks. The first level is kind of special for salt. So format of the image will be QQL2. The image, I'll use the juice image that we used before, so I'll copy the link. I'll place the disk in the default pool, default storage pool, and I can also provide it a size in megabytes. Just be aware that specifying a size that is smaller than the template image will do nothing. Now we can also add this network interfaces. They also have names, even though it's not written in the libvirt XML definition. They also have a type, so most of the time here I'm using the network type because it uses a defined libvirt network. The network that we'll use here is named default. And we also want to have some graphical display of type VNC. And we also want to set the seed flag to false. It normally adds the salt minion configuration, but it needs patches that are pending review upstream to work. So we'll just save. Now we will apply the state. Salt. We'll define the host name, which is the minion name, kvm1.hol-1313.net. I can replace the hol-1313.net by an asterisk, just faster, and matches more values. In here is not that interesting, but we can see later that we can run commands on multiple virtual hosts at the same time. State.apply, and the name of the state is VMs without the .sls extension. So now our VM is defined. We can run salt kvm star, so we'll see that what will happen. Virt.list active VMs. So this is listing all the running VMs on every minion that has a name that starts with kvm. So you see that we have none on kvm2, and we have VM1 and VM2 that are running on kvm1. Let's see in the console. Here we have the VM2. If we check the graphics, it runs the first boot wizard. So in next exercise, we'll improve our template to get rid of the first boot wizard. Before continuing, we want to remove the VMO2 virtual machine because we'll just improve our state and create it another time. We can do it either using the command line or using the UI. We'll do it with the UI for now. And the VM has disappeared and the disks have been removed. And now we will need to change our template to customize the disk template image. Here it's an HTTP link, HTTP image, so we need to cache the image first. To do this, we will just add another state. Here we'll name it image cached. We'll use the salt state that is called file.managed. The name of the state of the file will be temp /15 sp1 kvm and zen.qcal2, for example. And the source will be our remote URLs. Since it's a remote URL, file.manage will try to match a checksum. Since I don't have a checksum here, I'll add the skip verify and set it to true. So now we have the image cached. We will need to customize it. Before continuing, let's go on the KVM1 machine. There is one tool that is shipped with the GuestFS tools that is called Virt Customize. So we can check the man page. And this Virt Customize will use an image, disk image, and it can perform any kind of action on that, like appending lines to config to files, or moving files, installing packages, setting host name, running commands, setting root password, etc., etc. So we will use this one. So for that, we'll create another state. Let's say image customized or something. And we'll run the command.run state. The name of that state will be multi-line, so in YAML is using that pipe symbol, and then going to the next line, indenting virt-customize, run command, for example, rpm-e, choose first boot. -a, here we'll need to pick up this file path. And for this state to execute, we need the image cached one to have been executed as well. So we add a require. The require needs a file, because it's the module here that starts the module, the state, file, and image cached, which is the ID. We also want to add a require here. So here is command module, and the ID is image customized. And in this one, the template image now we can add more to our customized Virt Customize. We can add a host name, pmo2-hol-1313.net. We can also add a root password, column Linux. Here it will set the root password to Linux. This is entirely unsecure. There is a better way to do it in Salt using encrypted pillars. This is documented on the web. We will not do it here just to keep things simple. But you can try it. We will also add the configuration for this registration by appending a line. So we will append to the file etc salt grains. First line is SUSE Manager. and we will add activation key. /15 sp1, and we will add another line, this time to etc sort minion.d master.com, and as the master is rv HOL-1313.net, just what we did before for VM1. Now we also need to run one command to start the salt, to enable the salt minion. System control enable salt minion. You see here that there's no need to add -- now to start the minion at the same time, because the VM is not yet running. So this will happen on the disk image in a special super minimal appliance, and it will shut it down after, but the salt minion will need to be started when running the VM after. So we'll just save and apply. There it is. So we can see that there is a more verbose output from our state. So first it executed the image cached. So it got the binary file. It ran the virt customize command. And here we have the output of it. Everything went fine. And the VM2 has been started. Let's see in the console here. The VM is started. I can log in with root Linux, no problem. And check in here. We have the salt key. All fine. This is good, but our state is meant only for one VM at the moment. It's pretty likely that we will want to reuse this state for other virtual machines with other configurations. So we will see now how to make it configurable and reusable. But before, we need to delete the VM02 machine because we will create it again. Salt kvm1. This time we'll do it using the command line, just to show you the second way of doing it. This is exactly the same thing that is called by SUSE Manager from the UI. So here we'll apply a state that is shipped by SUSE Manager, virt.deleted, and this one needs a pillar to figure out, to know which data to which VM to remove. A pillar is just like a Python dictionary. So here I will add the domain name property and VM02 because I want to remove that machine. And there we are. So this state is powering off the machine and then destroying it. Note that there is a difference in powered off and shut down. Power off is just like pulling the electrical plug from the wall. So we'll edit the vms.slash file again, and we want to add some variables in it. So we want to add run this state for multiple VMs, for example, and have each VM have a different name, have different CPUs, memory, have an activation key, maybe different, maybe not. So you can do this all using Jinja. And you have a lot of information here on this documentation page on Jinja. This explains all the specifics of Jinja for Salt. And here you also have all the Jinja language explanations, which are often useful to refer to. So here we want to have multiple VMs, so we'll add a loop. So a block will start by curly brace and %. For here I give the name of the variable, and it will be a pillar. So we'll get the data from pillar VMs and add a default value with an empty array. The end of the block will be at the end, and 4. Now we can change, for example, the VM name. Variables will be in double curly braces. Here the name is VM, and we will assume there is a name property in it, just like in normal Python. We'll do it here as well. And here. Since the VM may have different customization, we want to have the template image be different for each VM. This obviously may be optimized, but for simplicity, we'll do it this way. Okay, and we also need to change the requires to edit. Okay. Now let's continue with CPU, for example. CPU, easy. So VM, but here instead of using the square bracket, we'll use the get notation, the get call, get CPU, and we'll add a default value of 1, for example. VM get mem, and we can add a value of 512. Okay, can do it also for storage pool. Can add the default. And same for the interface. Okay, this is the easy part. Everything is templated. We can also here add some condition to to not always have the activation key. So this could be pretty interesting to set the activation key, or even to not add it at all. vm.get activation key. We'll just add a non-value. So if we have this and it's not none, then we can add the configuration and the salt minion. By default, Jinja will replace the if by an empty line. So we will just add a small dash here at the beginning and the end of the block to not have these blank lines. And here we can also replace that activation key by vm activation key. So now we'll try it out. Salt kvm1 again. State.apply doesn't change. VMs, okay. And here comes the difference. Pillar equals, and then we'll add our values. We had a VMs, which is an array, and in each of these items we have a dictionary. It has a name property, which is a VM02 in our case. We can add the activation key 1/15 SP1, and we could also add a CPU to have more, and we can also add different memory value. There we are. We'll just verify salt kvm1 vert.get xml vm02. So you see the 2 CPUs and the memory, 700 megabytes. So we have done our template. In the next exercise, we want now to use our VM state in the high state, in the salt high state. So we will do it for 2 VMs, to add 2 VMs on KVM2, one for database and one for a web server. So first we want to add the state in the salt state. For that we just need to add the top slash file that is an srv salt, and add kvm star VMs. So this will apply the VM state to all machines that are all menus that start with the kvm string. As of now, it will do nothing at all, just because we have no pillar data. To do this, we'll need, in this srv pillar, we'll need also some data. VMs data, for example, slash. And we add some Jinja here to make it conditional. So if the grains ID starts with KVM2, so we want that to apply only on KVM2, then we'll have a VM's property, and in that we have one VM that is named web with one activation key, one SLE 15 SP1. I'll use the default CPU and memory, and I can just copy that again for a DB VM. This is the first step, but it doesn't apply the VM's data yet. To do it, we need to also add a top.slash and SRV pillar, and it looks pretty similar to the one that is in SRV salt. So there is a base environment. I will apply it to all KVM hosts, the VM's data. So this will apply the VM's data state to all KVM minion. Now we'll see the high state for KVM2. KVM2 start state show high state. So here it is. You see the web image customized here that requires web image cached. Web image cache is here, etc., etc. You can see exactly the same things in the web UI. So this is in states. Oh, this is KVM1. We need to change to KVM2. States, high state, and here it gets the high state. And this adds to the other high state that you have with formulas and configuration and whatever. And you can apply the high state directly using the UI or from the command line. Let's do it in the command line. Salt KVM2 star state that apply. There we are, the state is applied. We can check virtualization. We have our two VMs ready. In this exercise, we will improve the DB and web VMs by adding a private network to them, and also by using a different storage pool than the default one. First, we'll create a state to create a storage pool. We'll create it in a test pool.slash file. We'll give it a name, test pool, and this one will run the virt.pool running state. So it is a different state that is ensuring that a storage pool, a given storage pool, is defined and running. We'll give it a name, test, a pool type. Here we'll use a dir type to find out more on all the types, the pool types and their configuration. You can refer to libvirt storage configuration. Target. This is where the images will be stored. So let's say pool SRV pools test. We want to say that this pool is going to be started automatically when the virtual host is running. And we also need to require the libvirt service to be started. libvirt service. So this part here, the libvirt service require here is only possible because of the virtualization host formula that we have applied. And this virtualization host formula defines the libvirt service, so we can use it in the high state. I also have provided a private network .sls file. I'm not typing it here. The reason is that the network definition state in SALT is not yet feature complete, and most of the time to get really customized networks, it is much better to go defining the XML. So writing an XML file. So here it defines the XML file here, and we'll watch for changes in that file, and every time there is a change, we'll destroy the network, but only if it's already active. No need to do it if it's not active. And it's the same. We'll undefine it, define it again, set it as auto start, and start the network again. So there is really a chain. Hopefully this will be going away as soon as the network defining states in SALT are improved. The names here are also mimicking based on the same pattern that the ones in the virtualization host formula, so that we can reuse private virtnet start. Here is just the network name, and then virtnet start is the command part to ensure the network is started. Now we'll just change the pillar. Serve pillar VMs data to add here the pool test to both VMs. We also need to modify the VMs.slash file to ensure that this pool will be started when creating a VM. So here we will add a virt vm.get pool default pool. Now we will add again the pillar to add the networks. Pillar VMs data net, but instead of adding just one, we'll add two, one default and one private, because we want still the default for our machines to be accessible from the outside, and for private to ensure safe communication between the web and the database server. But then we'll need to also change our VM state, because it only handles one network. So here we'll need to add a loop. For net in vm.get net. We'll add default, one network as default. The end of the loop will be here, and here we need to replace a 0 by a special value, which is a loop.index0. And here we need to replace it by net. We also want to add more requires here. And for it's not vert, it's a command, and the name is net vert net start. Since there are states that are defined in other files, we will need also to add include here at the top. So include test pool and also private network. Now we will destroy the VMs, the two VMs. Delete as well, and we will apply the state again. This time we'll do it this way. So we need to check. So we have interface ETH0, which is default, and ETH1, which is private. We have test pool. Now the state is applied. We can see our two VMs. Salt kvm star vert list active VMs. There we can see all our VMs. Now we'll need to accept the salt keys of the virtual machines that we created during the previous exercises so that they can be used for monitoring later on. And now all systems are in.
Hi everyone, welcome to the second part of our hands-on on how to monitor virtual machines using SUSE Manager. I am João Cavalheiro, Engineering Manager in the SUSE Manager team, and on this part I will present about Prometheus and Grafana and how SUSE Manager can help setting up monitoring on your infrastructure quickly and easily. The exercise in the end will follow up on Cedric's work and will use the virtual machines that were created on previous steps. SUSE Manager can help you automating your monitoring in a secure and easy way. The central role of SUSE Manager in a monitoring infrastructure is to provide configuration automation, which includes centralizing and simplifying how to set up Prometheus exporters on managed systems. You can centrally define which systems you want to monitor, which alerting rules you want to use, and also deploy Grafana dashboards. SUSE Manager includes self-health for the server itself and a set of pre-configured Prometheus alerts. You can set up Prometheus and Grafana servers with a few clicks and use the provided dashboard templates to get started with your monitoring on your infrastructure. Prometheus is an open source monitoring toolkit with a very active community. It has a multidimensional data model with time series data and a powerful query language. There are exporters available for all the popular application stacks, which allow you to plug monitoring on almost any existing system with minimal changes. And Grafana comes up as a natural complement to Prometheus due to its powerful data visualization UI. It allows you to combine data from Prometheus with other sources, for example PostgreSQL, and there is support for a variety of graphs, as well as many example dashboards available to use as building blocks in almost any popular application stack. The monitoring exercise will have three main parts. First, we will set up a monitoring server with Prometheus and Grafana using salt formulas. Then we will configure the SUSE Manager server self-health and see some insights on Grafana. And on the last part, we will use salt formulas again together with system groups to enable monitoring on all virtual machines and view the metrics in Grafana. Here we have SUSE Manager with all the VMs created during the previous part of the exercise with Cedric. To continue with the monitoring exercise, first of all, we will need to onboard the monitoring VM. And to do that, we need to accept its salt key. Our monitoring VM is now onboarded. This VM is where we are going to run Prometheus and Grafana. To install Prometheus and Grafana on this VM, we will use salt formulas. To do so, I enable Prometheus here. I go into this tab. And on the Prometheus formula, the important thing to look at is the username and password. Those will be used by this Auto-Discover Clients option to allow the recently created Prometheus setup to be able to access your SUSE Manager server via its API and get information about the monitored systems. It's important to use some credentials here that have access to the API, maybe not your admin user, but a user that has visibility over the organization part that you want to monitor. You also want to make sure that alerting is enabled. We'll look into this later in more detail. And you can save the formula and apply the high state. While we wait for the high state application to complete, we'll look into the Grafana formula. Here you can enter the credentials you want to use on the Grafana UI. Those will be used to log in Grafana exclusively. For simplicity, I'll use admin. And you can enter the data source you want to use. How should it be named and in which URL it is. Since on this exercise we will have Prometheus and Grafana running on the same VM, there is no need to change the default value. And below you can select which dashboard templates should be deployed. We'll use the default ones, which include the server self-health, dashboard to monitor the clients, and the dashboard for Apache and HTTP servers. There are some Kubernetes dashboards that we now include in SUSE Manager, but we won't be using those as part of this exercise. So next we save the formula and we apply the high state again. You could have done those two operations in a single high state application if you were to set up the Prometheus and Grafana servers on the same machine. Here on the exercise, just to demonstrate separately how they work, I have applied the high state twice, but this is not necessary. Once the high state application completes, we'll have our monitoring VM up and running with Prometheus and Grafana. So next, to be able to see some metrics, the thing we'll do is enable the SUSE Manager self-health. This can be done on the manager configuration under admin. On the monitoring tab, you can see what is the current status of monitoring. By default, the self-health is disabled, so you need to explicitly enable it here. And also those ports where the exporters will run will have to be exposed on the SUSE Manager server. So they have to be open on the firewall so that the Prometheus server can scrape metrics from SUSE Manager. I will now enable monitoring. This will require a restart of Tomcat and Taskomatic. In the meantime, our high state application on the monitoring VM should have completed. Let's take a look. Okay, no errors in the log. So now we will be able to go to this URL, port 9090, which is where Prometheus runs by default. And we see that we have now the Prometheus UI up and running. Here in Prometheus, we can take a look at the list of targets, which is the list of endpoints that we are monitoring with Prometheus. You can see that all of them are up. Those 6 endpoints here below Manager server are the SUSE Manager self-health endpoints, where we are collecting data from a node exporter, from PostgreSQL exporter, and from other metrics coming from SUSE Manager internals, from or about both Tomcat and Taskomatic. You also see here there is this additional endpoint below, which is Prometheus monitoring itself, and a list that has 0 systems at the moment called Manager clients, which is where our monitored client systems will show up as soon as we add monitoring capabilities to them. On Prometheus, you can do some quick queries, like for example, checking which endpoints are up. You can also do more interesting things directly on the UI, like checking what is the amount of memory that my server has. I'm not doing any filtering here to get this metric, because so far I'm only collecting data from a single node exporter. But if I want to have a more comprehensive filtering to get data from a specific instance, I can filter for those labels here. We can also, in this case, simplify a bit the result. Prometheus allows you to do some maths directly on the expression. In this case, I want to divide the result by 1024 squared so that I get the value in megabytes. Now this becomes much more interesting when you see this, when you look at this in a visual way. And for that purpose, we'll now look into Grafana, which should be running on this same machine on port 3000, which is Grafana's default. For now, we don't need to log in, so we won't still be using those credentials we defined while we were setting up the formula. We'll, for now, just take a look at the SUSE Manager server dashboard, which is shipped as a template. So this is what you get after applying the formula. You can see that we have here some insights about how the system is behaving and how the operating system is also behaving. You can see below some internals about JVMs for both Tomcat and Taskomatic, some insights on how the database is looking, and information about Taskomatic scheduler, among others. I will now get back to SUSE Manager to add monitoring on client systems. I will first do this on a single VM, and again I will use a salt formula for that. So we'll use this VM01, and now I will select the Prometheus exporters formula. As with others, you now have this extra tab where you can see the settings. And here we are going to enable only the node exporter. Later we'll see how to use Apache exporter and Postgres exporter on our web and DB servers respectively. For now we'll just use some basic monitoring here on this VM. So we'll again save, apply the high state. As soon as the high state application completes on this system, it will start exposing metrics. However, in many cases, your systems are behind firewalls. And in order to be able to collect metrics, Prometheus needs to access the monitored systems. The Prometheus node exporter is publishing the data by default on port 9100, as you have seen while we were configuring the formula. And since our VMs are running SLE15 SP1 that has firewall-D enabled, we'll need to open this port on all the VMs. There are several ways to achieve this, but on this step we will be using configuration channels, which is a feature provided by SUSE Manager, which allows you to add a salt state to this configuration and then apply that configuration to a system or a group of systems. To create a configuration channel, we supply a name. And we define a salt state. So we want to make sure that our firewall is active and configured to allow Prometheus to scrape whatever is, in this case, on port 9100. Be careful with the state here, as this is YAML, so it's sensitive to spaces. So we have created this configuration channel, and now we just need to add systems to it. Let's add our VM01, but also the other VMs, since we'll need to apply this to all of them. This could be done using a system group, but I haven't created the system group for those VMs yet. Anyway, it will work the same way. Okay, so our configuration channel is created. We can now get back to our VM01. And if we look here into states, we see that there is this configuration channel assigned to this system, which means that the next time I apply the high state, this system will have its firewall configured to accept incoming connections on port 9100 so that we can scrape Prometheus metrics. So on our Prometheus UI, we can now see this system in the list of targets. And now that this system has its metrics being collected, we should also be able to see it on Grafana using one of the dashboard templates that are provided, which is dashboard for client systems. As you see here, we are now collecting a few metrics about this system, which include hardware basics, so mainly the metrics that Node Exporter provides. This is a very simple dashboard. It's meant to be a template. You can extend it and add extra panels here and customize it as much as you want. We enabled monitoring for a single system. So as you can see, that is the only system we have here on Grafana. No groups. This is because we also have no groups defined on SUSE Manager. When you define system groups and add systems there, the Grafana dashboard template will reflect that configuration. So let's see that in action. I will create a system group and we'll put my VMs inside that system group. So on this group, we want to add VM1, VM2, and we will also add our web server and our database server. This is the group where we will want to add monitoring, basic monitoring on all systems. So node exporter is what we want to have running on all of them. Later we will see how to add other exporters to the database server and the web server. For now, all we want is to get basic insights. So for that purpose, I will again use the Prometheus exporters formula. Make sure that the settings are correct. So we want only the node exporter running on the default port. So I can save the formula and apply the high state. This will apply this high state to all the VMs on this group, and once it completes, they should all be running node exporters, and we'll be able to see that in Prometheus. The high state application has completed, so our systems that are part of this group should now be visible in Prometheus in the list of targets. They are all up, so it means metrics are now being collected. And if we look at Grafana, our client system's dashboard now shows the group. So you can select the different groups if you have more than one system group in SUSE Manager, and the list of systems that are part of that group. So all our VMs are now monitored, and the metrics are all in Grafana. Next, we will add PostgreSQL Server to our DB VM. We will again use a configuration channel to define the profile of a database server. So let's call it PostgreSQL. Here I will use a predefined salt state, as it is much bigger than the previous ones we have used. I will quickly explain what it is about. So it will make sure that PostgreSQL and SQL Server packages are installed, that the PostgreSQL service is running, and that we have the basic configuration in place, which includes the PostgreSQL data directory. It includes setting the HBA and pgconf files to accept connections from the outside, and using MD5 authentication, not just ident authentication, and to create a test user and a test database. Now that the configuration channel is created, I can assign it to our database VM to make sure it gets configured to run PostgreSQL. And I will also enable the PostgreExporter formula on this VM, so that when we apply the high state, this VM will not only get PostgreSQL running there, as it will also get the PostgreSQL exporter. For that purpose, we need to configure this based on the credentials we defined on the configuration channel. The user is called myDatabase, as well as the password and the database name for simplicity. We'll use the default listen address, save the formula, and apply the high state. So once the high state application completes, we can get back to Prometheus, look at the targets, and see that we have here a new target on our manager clients list, a new endpoint, which is the PostgreExporter running on our database VM. This information here just shows that the exporter is up. It's not providing any insights on the Postgre database itself. We can do a quick check here. There is now this metric. You have two entries as a result because there is a PostgreSQL server running on SUSE Manager server, which is the second item you see here. This one is available since we have set up the server self-health. And now we have this other entry, which is relative to the database we have just set up in our DB test server. Also, if we go into Grafana now and open the PostgreSQL database Insights dashboard, we see that this is now available here on the list. So we have this database server not doing anything at the moment. There isn't any activity on that database, but you can already see the basic Postgre activity going on. And if you generate some load on this database by doing some queries, you will see this dashboard being affected in real time. So this is about database monitoring. You could apply a similar recipe to create a web server and have it monitored with the Apache exporter, but I'm not going to cover this on today's exercise. So this is the final stage of our monitoring exercise. So thank you all for watching, and happy virtualization with monitoring.